Welcome back to Daily Dose of Space. When people look at the night sky, there is a quiet assumption hiding behind that view. The assumption that what we see around us is normal, that our cosmic neighborhood is just another random patch of the universe, no different from countless others scattered across unimaginable distances. For most of modern astronomy, this idea felt safe, comfortable, even necessary. But over time, as telescopes grew more powerful and our maps of the universe became more detailed, that assumption began to feel less certain. Not dramatically wrong, not obviously false, just slightly off, as if something about our place in the universe didn't quite line up with what the equations expected. This episode is about that discomfort, about the growing suspicion that we might live in a region of the universe that is unusually calm, unusually empty, and possibly not representative of the cosmos as a whole. The comfort of average. Cosmology relies heavily on averages. When scientists describe the universe, they talk about average density, average expansion, average temperature. These averages allow a universe that is messy on small scales to become predictable on large ones. Galaxies cluster here, voids appear there, but overall, everything balances out. This thinking led to the cosmological principle, the idea that the universe looks roughly the same everywhere if you zoom out far enough. No special directions, no special locations, no cosmic privilege. It is an elegant idea, and for a long time, it worked remarkably well. Early observations supported it. Large galaxy surveys showed a cosmic web that looked statistically uniform. Tiny fluctuations existed, but nothing alarming. Our region seemed comfortably average, exactly where it should be. But comfort in science can be dangerous, because the more precisely astronomers measured the universe, the more that sense of average began to feel like an assumption rather than a proven fact. A slightly empty neighborhood. As galaxy maps grew larger and deeper, astronomers began to notice something subtle but persistent. The region of space surrounding the Milky Way appears to contain less matter than expected, not dramatically less, not enough to be obvious at first glance, just enough to be noticeable when statistics became precise. This region stretches across hundreds of millions of light years and contains fewer large galaxy clusters than models predict. It is not empty space, but it is quieter than average. Astronomers often refer to it as part of a larger local void, a vast underdense region embedded within the cosmic web. What makes this unsettling is not the existence of voids themselves. Voids are normal. What raises eyebrows is our apparent position within one. We do not seem to sit near the edge, where such effects might be minimal. We appear to live deep inside it, and that raises a difficult question. If our local environment is unusual, even slightly, how much does it affect what we think we know about the universe as a whole? Expansion seen from the inside. The universe is expanding, and galaxies are moving away from each other as space itself stretches. Measuring the speed of that expansion has become one of the most important tasks in modern astronomy. But there is a problem. Different methods give different answers. When astronomers measure expansion using nearby galaxies, they consistently find a faster rate than when they measure it using the early universe. This disagreement, known as the Hubble tension, has become one of the most stubborn puzzles in cosmology. One possible explanation does not require new physics or exotic energy. It requires perspective. If we live inside a region with less matter, gravity pulls less strongly on nearby galaxies. With less gravitational resistance, space expands slightly faster locally. From inside such a region, the universe would appear to be expanding faster than it truly is on average. This does not mean measurements are wrong. It means they may be incomplete. The uncomfortable implication is that our location might be quietly influencing our conclusions. When assumptions start to crack. Cosmology depends on the idea that local observations can be generalized, that what we measure here applies everywhere. But if our region is not representative, then even our best measurements must be handled with caution. This does not immediately invalidate existing models, but it weakens their foundations. A universe that is mostly uniform but locally uneven becomes harder to interpret. Small biases, when projected across billions of years, can produce large misunderstandings. Scientists are careful here for good reason. Declaring our location special risks sliding backward toward outdated worldviews. But ignoring evidence simply because it is uncomfortable carries its own risk. The truth may lie in between. Our location might not be unique, but it may not be perfectly average either. A universe that selects its observers. There is another layer to this story that rarely appears in equations. Intelligent observers require stability. Long-lived stars, predictable environments, time, regions of the universe that are extremely dense, violent, or chaotic may simply not allow complex life to persist long enough to observe anything. Calm regions with fewer catastrophic events offer a safer stage for complexity to emerge. This introduces a subtle selection effect. Observers are more likely to arise in regions that are quiet enough to allow them to exist. That does not make those regions typical. It just makes them observable. In that sense, our calm neighborhood may not be an accident, but a prerequisite. We do not observe a peaceful universe because the universe is peaceful everywhere. We observe it because only peaceful regions produce observers. Once this idea is considered, it becomes difficult to treat our perspective as neutral. Mapping beyond our bubble. To resolve this question, astronomers are pushing observations far beyond our local environment. New surveys aim to map tens of millions of galaxies across enormous volumes of space, reducing the influence of local irregularities. The goal is simple in principle, but difficult in practice. To see the universe as it truly is, scientists must observe regions so distant that our local environment becomes irrelevant. Only then can they test whether our neighborhood is typical or quietly misleading. At the same time, improved simulations are exploring how cosmic structures evolve differently depending on environment. These models suggest that even modest differences in density can shape cosmic history in subtle but powerful ways. The universe, it seems, may care deeply about context. Living with uncertainty. Perhaps the most important lesson of this mystery is humility. The universe does not guarantee that our viewpoint is fair. It does not promise that the sky above us tells a complete story. Science progresses by questioning assumptions, even comfortable ones. The idea that we live in a perfectly average region may turn out to be mostly correct, slightly wrong, or fundamentally misleading. Right now, no one can say with certainty. What is clear is that perspective matters. Where we stand in the universe influences what we see, how we measure, and how we interpret reality. Our corner of the universe feels calm, balanced, and familiar. It feels like a reliable reference point, but that calm may be deceptive. It may be the result of cosmic geography rather than cosmic law. Understanding the universe may require more than better telescopes. It may require accepting that our view is shaped not just by physics, but by position, and that somewhere beyond our quiet neighborhood, the universe may look very different from what we have come to expect.